Hi, I'm Kemil, and this is Chem with Chem. Now, in this session, we're going to be going through question 1 of Chemistry Paper 2 from the January 2022 sitting. If this is your first time to the channel, then welcome. We do sessions like these where we go through exam papers from the CXC exam, and we also have chemistry experiments where we look at experiments that are required for CSEC. And we also look at common errors that are made during the exam. So just check out the channel, look at the other videos, and be sure to leave a like if you like them, share them with your friends, and also consider subscribing. I hope you find value in this, and be sure to turn on post notification when you subscribe so you will not miss any time we upload new content. It is recommended that we do not spend more than 30 minutes on question 1. A student conducted an experiment to investigate the reaction between calcium carbonate and dilute nitric acid. He weighed 1.8 grams of powdered calcium carbonate, very important word right there, powdered, and allowed it to react with excess dilute nitric acid. Excess dilute nitric acid means that all the calcium carbonate present would have been used up. The volume of gas produced at 10-second intervals was measured for a total of 80 seconds. Table 1 is a record of the volume of gas produced from the reaction. That's with the powdered calcium carbonate. Figure 1 is an incomplete diagram of the arrangement of the apparatus used in the experiment. And we're going to be coming back to table 1 in a little while. So we are asked now to complete figure 1. Complete figure 1 by drawing and labeling the remaining apparatus to show how the gas was collected and measured. All right, so we're going to be drawing what's missing from this apparatus that's here, and this is going to show how the gas was collected and measured. Very important word there, collected and measured. So what's missing? Let's get right into it. This is for the thistle funnel. Doesn't play a big role in measuring, but it plays a big role in releasing the amount of acid needed, even though we're seeing where everything is already in the container or the conical flask. This is our delivery tube, which would take us to our gas syringe. And we should use a pencil and ruler to do this, but given the medium I'm using, all right, so this would have to be sealed. Can't seal after we've added. The whole system would have to be sealed. The calcium carbonate powder would have had to be in the flask, and then the acid is added from here, from the thistle funnel. So this is the setup. So we're just going to label. So this is our thistle funnel, and this differentiate right there. So that's our rubber bung. And this over on our right is our gas syringe. And we don't need to say it's graduated. That would probably be over answering. So this is our gas, that's our gas syringe. And that should give us the 3 marks there. So that's what's missing from the diagram. Okay, so we're at part B. Using the axes in figure 2, plot a graph on page 5 showing the volume of gas produced versus time for the reaction of dilute nitric acid with the powdered calcium carbonate. Label this graph A. What's very important before we even begin to plot is to ensure that we know the scale on each axis. So looking at the x-axis, we see that each centimeter is used to represent 5 units. So that's 5 seconds. right? So we're going up 5, 10, 15, 20, and so on. So it means each millimeter, then each of the smallest square that is present is representing 1 second. Now on the y-axis, we're seeing where 1 centimeter is being used to represent 25 units. That's 25 centimeters cubed. So it means that each of those tiny, or each of those 1 millimeter square is representing 5 centimeters cubed. So let us plot. So the first point is plotted for us. So we're going to go right ahead into the second one. So at 10 seconds, we have 100 cm cube being produced, of gas being produced. So we'll find 10 on our x-axis, and we're going to go up. This is where 100 is. Right, so that's the first one. At 20, we have 190. So 20 is here. We're going to find 190. 90 is here. 30, 250. That one is an easier one. 40, 280. 50, 320. 60, 340. 60 is 340. So here we go. This is the right here. 70, 360, and at 80, 360. So we see that things have leveled off. So after 70, no more gas was produced. We're getting a leveling off to say that the reaction would have stopped at 70 seconds. All right, so we're not finished. We would have plotted. We now need to connect these points that were plotted, and we're going to do this using, it's going to be a curve. I'm not going to use a straight line. So we're going to do it free-handedly, and we should get a nice curve. So let's just get that going. All right, there we are. So that is what we want, and we should label this one. I said we should label this graph A. So we'll call this graph A. Okay, part C, write a balanced equation including state symbols for the reaction between calcium carbonate and the dilute nitric acid. Okay, we get a mark for having the correct state symbols, so that's very important. So this is what we have. Calcium carbonate, CaCO3 solid plus HNO3 aqueous, it's an acid. All nitrates are soluble, Ca bracket NO3 bracket 2 aqueous plus CO2 gas plus H2O, which is a liquid. All right, so let's balance. We have 2 nitrate here, so we need 2 in front of the nitric acid, and everything is now balanced, and that would give us 3 marks. Now, part D, calculate the volume of gas that can be obtained from reacting 1.8 grams of calcium carbonate with dilute nitric acid at RTP. And we're told 1 mole of gas occupies 24,000 cm cube at RTP. That's the molar volume at RTP. And we're given the RAM for, carbon, oxygen, calcium. So we're just going to work with that. So looking at this equation, the equation is going to guide us here. We don't see a number in front of calcium carbonate, so we know 1 is there, telling us that 1 mole of calcium carbonate reacts with 2 moles of nitric acid to give us 1 mole of calcium nitrate and 1 mole of carbon dioxide. We're going to ignore the water for now. 1 mole of water is produced. So we're concerned about calcium carbonate and volume of gas. So we know that for every 1 mole of calcium carbonate, we end up with 1 mole of carbon dioxide, which has a volume of 24 cm³ at RTP. So for the first mark, well, we could write a statement that says 1 mole of calcium carbonate produces 1 mole of carbon dioxide. Better yet, 1 mole of calcium carbonate has a molar mass of, well, we need to find that first. We're given the RAM, so we're just going to use that to find the molar mass of calcium carbonate. Of course, we're going to express that in grams per mole. So we have 1 calcium, so that's 40 plus 12 from carbon, and we have 3 oxygen, 316, 48. I like this one because it gives 100. So 100 grams is the molar mass. 100 grams per mole is the molar mass for calcium carbonate. So we can now say that 100 grams of calcium carbonate reacts to give us the 1 mole of carbon dioxide, but we know that 1 mole of a gas occupies 24,000 cm³ at RTP. So this is the volume of gas that's produced from the 100 grams of calcium carbonate. Now, if we use 1.8 grams of calcium carbonate instead of the 100, we need to find out what volume of gas, carbon dioxide, will be produced. So we're now going to cross multiply. Of course, when we do that, we're going to have 100 grams times x is equal, we're going across diagonals, 1.8 grams times 24,000 cm³. We're going to divide both sides by 100 grams to make x the subject. And when we do that, we're going to end up with x being equal to 432 cm³ of CO2. And that would give us our 3 marks. From the graph, the total volume of gas produced is 360 centimeters cubed. Calculate the difference in volume between the answer obtained in D and the total volume produced. Suggest a possible reason for the difference. Now, so here it's simple math again we're going to show. All right, so from the calculation just now, we expected 432 centimeters cube of gas to be formed. So theoretically, we expected 432 cm³, but in reality, according to the question, 360 cm³ of carbon dioxide was actually produced. So they want us to calculate the difference, so we're just going to state that 432 cm³ minus 360 cm³, and the difference there is 72 cm³. And so we should suggest a possible reason for the difference. Now, a possible reason for the difference why we did not have all of 432 being produced, it could be impurities. Impurities could have been present in the calcium carbonate sample, right? And if impurity is present, it means that we don't have 100% purity of the calcium carbonate, so we would not get the expected volume of gas or the expected amount of products formed. Now state 3 factors that can affect the rate of reaction between dilute nitric acid and calcium carbonate. Not factors that affect rate of reactions in general, but the factors that could affect or can affect the rate of reaction between dilute nitric acid and calcium carbonate. So of course, temperature is one. Pressure does not apply here. So temperature is one, surface area is another, and we could have concentration. Of course, the concentration of the nitric acid in this case. And that would give us 3 marks, just like that. G, if marble chips That's large granules of calcium carbonate were used instead of powdered calcium carbonate. Sketch a graph of what this reaction would be on figure 2 on page 5. Label the sketch graph B. So if we had used large granule instead of powder, we would have less surface area exposed, so we'd expect a slower rate of reaction. So to show a slower rate of reaction, we just need to show a curve or a graph that is not as steep. So let's look at what our sketch would be like. So let's go right ahead and just sketch what the graph would look like if we had used granulated calcium carbonate or marble chips with smaller surface area. So this is what our sketch would look like. All right, so we're seeing, let's look at the similarities, well, in anticipation of question H. So let's just look at the similarities. The final volume of gas produced is the same. What's different though is the time taken. We see that for graph A, we really should label graph B. That's granulated CaCO3, and this one is powdered. All right, so we're seeing that the final volume it produced is still 360 centimeters cubed, but we're seeing that this volume was produced. We're seeing that the powdered calcium carbonate produced this volume faster than the granulated calcium carbonate, and also there's a steeper slope for graph A, and this tells us that the rate of reaction was faster. So we can think of this as a slide. Whichever one would get you sliding down faster is the one with the faster rate. So we're seeing that the initial rate here for A is higher than that of B. It is steeper, so that's a difference. Okay, so here we're asked to complete the table below by identifying one similarity. So we just went through the similarity and the difference between graph A and graph B, and we're asked to suggest one reason for each. So we're just going to write them in. We just discuss them. So the similarity is that both of them tapered off at the same value. So both tapered off at the same value, meaning both produce the same volume of gas. So both graphs tapered off at the same volume, or they show that 360 cm cube of CO2 was produced. And the reason there would be that the same mass was used, so the same volume would be produced. So even though one was granulated and one was powdered, the same mass was used. So the same mass of calcium carbonate was used in each reaction. So it follows we would get the same volume being produced. The difference, there are two. The difference is for graph A, we see where the volume of gas produced happened faster for graph A versus graph B. Or we could state that the initial rate of graph A is faster, or the slope of graph A is steeper than that of graph B. And this is showing us that the rate of reaction for powdered CaCO3, which was used in A, was, that's WAS, was faster due to larger surface area resulting in more collisions. So anything that results in more collision, anything that increases the frequency of collision will result in a faster rate. So that's it, 25 marks. Please check out the card for number 2. So we've come to the end of today's session. If you found value in this, please like and share and leave a comment. Thank you for joining Chem with Chem.